Hi girls, in this video I'm going to take you through the start of the alcohols topic. In this video I plan to look at naming alcohols first of all, which is again really part of unit 2.2, but I like to look at naming these molecules as we go along in the different families, and then we'll put that all together in 2.2. But then we will also have a look at the first 3 points of this specification. So look at sort of physical properties of alcohols based on their hydrogen bonding. We'll look at the structure of alcohols, primary, secondary or tertiary. And then look at the preparation of alcohols very, very briefly. And then what that means is that we will only have to look at the reactions of alcohols, which is relatively brief to do. There's no mechanisms or anything like that, so that's the good news. So over on page 2, you have your SEA definitions, which we will meet throughout the topic. It's important, as always, that you know these definitions well and can quote them word for word, as they're easy marks in an exam. So let's have a look at the basic structure of alcohols first of all and their general formula. So alcohols, what defines them and what puts them in a family together is their functional group, which is the C-OH bond, and the OH group is called the hydroxyl group. That makes alcohols more reactive than alkanes, for example. So at some point in your chain, you will have, and it could be in the middle of the chain or the end of a chain, you'll have a carbon that's bonded to an oxygen by a single bond, and then that's bonded to a hydrogen. Notice the bent shape around the oxygen due to the lone pairs on the oxygen. And obviously your carbon atom would have 3 other bonds, and that could be 2 hydrogens or other carbon alkyl groups to be part of the chain. So that OH group can be anywhere in your alkyl chain. And general formula of alcohols is CnH2n plus 1 OH. And so again, if you think about alkanes, they were CnH2n plus 2, and so what we've done is we've taken a hydrogen off and replaced it with this hydroxyl group. Again, sometimes the general formula is referred to as ROH, where R is the alkyl chain. So for example, CH3 is a methyl group, and that would lead to methanol, and then OH is obviously your hydroxyl group. So what I want you to do in this table is to draw in write in the molecular formula for the first 6 alcohols. And we'll just keep this where the hydroxyl group is on carbon number 1. That can vary, but we'll keep it as the sort of primary alcohols of each of these alcohols for now. So the molecular formula and then the structural formula. So the first alcohol in our series is going to be called methanol. So notice how the meth bit means that there is 1 carbon, and then the anol bit refers to the fact that it's an alcohol. So following your general formula, you would see that Cn is C1, but we don't include 1s in formula, so that's just going to be C. Then H2n plus 1 is going to be H3, and then our OH. And that's the way we would write our molecular formula. And you might think, well, why do we not just write it CH4O, putting all our hydrogens together? But really what we want to do is show that OH group at the end of the formula to show that this is an alcohol, to show that the OH is bonded together as part of a group. Structural formula, remember, shows all the bonds. So we've got our CH3 group. So that's carbon, single bonded to 3 hydrogens. Then we've got our O and our H. And again, notice the bent shape around the oxygen because of the lone pairs. Those oxygen atoms will have 2 lone pairs, which causes that bent shape around that oxygen atom. So do show that in your structural formula. And where at GCSE, sometimes it was okay to write your OH group together, and that's not accepted at A level. You must show every single bond, which includes drawing your oxygen-hydrogen bond within your alcohol molecule. So with ethanol, obviously you've got 2 carbons. So really with these, you're just changing your carbon chain. So that's where N equals 2, and the anol is referring to the alcohol group. So if we were to draw our ethyl chain, that's going to be C2H5, obviously leaving room for the OH group at the end. What's our molecular formula? We write that as C2H5OH. What I'd like you to do is to continue on with propanol, butanol, pentanol and hexanol. And technically with these, we're going to be doing the primary version of them. So just draw them where the hydroxyl group is on carbon number 1, as we have done with methanol and ethanol. So if you pause the video, take time to fill that in, and then I'll get you to check that. I'll fill them in and you can check them after. So you'll see I have written in the rest of the molecular formulas and the structural formula. And the ones we've drawn from propanol onwards, we technically speaking need a locant number for the position of the hydroxyl group. So what we have technically drawn here is propan 1-ol, and we'll look at naming that in a second. So propan 1-ol, butan 1-ol, pentan 1-ol, and hexan 1-ol, because the position of that hydroxyl group could vary when we get to 3 carbons onwards. For methanol and ethanol, we don't need a locant number for the OH group because it's always going to be on carbon number 1. So what I'd like to do now is have a look at naming alcohols. So maybe alcohols that have branches in the chain or different substituents, or the hydroxyl group is not on carbon number 1, that sort of thing. So I would say these are probably most similar to the IUPAC rules for naming alkenes. The rules are all the same, except we would replace the ENE at the end of the name with OL, because we're obviously naming alcohols now rather than alkenes. So you'll see that pattern hopefully coming up through these rules. So let me just take you briefly through these, a lot of these that you've met before. So first of all, what we're going to do is find the longest carbon chain, but it must contain the hydroxyl group, the OH group, because with any of our naming of our organic molecules, the longest chain must contain the hydroxyl group. So even if it's not the longest carbon chain overall, it must contain the functional group. And that determines the ending of the name, so whether it's methane, ethane, propan, and so on. What goes at the end of the name is the suffix OL, so rather than ENE for alkenes or ANE for alkanes, it's OL to indicate that this is an alcohol. Then we number our carbons so that the hydroxyl group is on the carbon of the lowest number possible. So even if you have other substituents like methyl or bromo groups or things like that, then you must make sure that the hydroxyl group, the functional group, is on the carbon of the lowest number possible. Number 4 then, the number indicating the position of the hydroxyl group appears between your prefix, like so your methane or your propan or whatever, and the suffix OL. And it should be separated from the prefix and the suffix using dashes. So for example, propan 2-ol. So this is a bit like saying but 2-ing or pent 1-ing with our alkenes. If we have more than one OH group present, then we should use the little prefixes di, tri, and so on before the suffix of OL. So for example, if we had 2 OH groups, it would be diol, or 3 alcohol groups, OH groups, it would be triol. And also a bit like with alkenes, if you remember, we would have gone from, say, but 1-ing to buta, 1,2-diing. With alcohols, we don't put an A in front of your carbon chain prefix. We actually put an E in front of the carbon chain prefix. So say, for example, if we had the following molecules, so you can see here, this is an ethane alcohol, but we have 2 alcohol groups on your carbon atoms. So this would be ethane. So notice how we have added an E there, dash 1, 2, so indicating that these OH groups are on 1 and 2. If they were both on carbon number 1, it would be ethane 1,1-diol. So we've transformed this name into ethane 1,2-diol. So we do need a positional number or a locant number now, because there's 2 hydroxyl groups, so it could be on both on carbon number 1, or 1 on 1 and 1 on 2. Then if we have substituents, then we must put those in alphabetical order. So even if their locant number is higher, then you must put them in alphabetical order, just as we've seen before. If multiple of the same substituent appears, use the prefixes di, tri, tetra, and so on. And then numbers are separated from words with dashes and numbers from numbers with a comment, as we said before. Just a little extra note on our locant numbers. We don't need those with methanol and ethanol. Though that is only if ethanol, if there's one OH group. But if there's two OH groups, as we saw above with ethane 1,2-diol, then you do need a locant number. And then in terms of drawing the structure of your alcohols, if you're asked to draw the structural formula, you must draw the OH group as the full structural formula showing all the bonds. But if you're just showing different isomers, then it is okay to group that together, OH, as long as you're not asked for the full structural formula. So if you're asked for the full structural formula, make sure you draw all of the bonds, which is O single bonded to H. So what I'd like you to do is try the examples on pages 5, 6 and 7. So looking at the molecules that you have there, what would their names be? So let me do the first example with you. So remember, the first rule is find the longest carbon chain that contains the OH group. So that longest chain must include the carbon that is bonded to your OH group. Okay, so there's your longest chain, and you can see that's 4 carbons, so that's going to be butane, will be the prefix of the ending of their name. We then number our carbons so that the OH is on the lowest possible carbon. So we're going to number that right to left so that the hydroxyl group is on carbon number 1. There's no substituents to consider here, so this is simply called butane. No need for an E because there's just one hydroxyl group, then a dash, then 1 indicating that the OH group is on carbon number 1, then another dash, and then OL. Butane 1-ol. So what I'd like you to do is to complete the rest of the examples on page 5. And then if you replay the video after you finish the examples on page 5, these should be fairly straightforward. This is just moving about the OH group. But then moving on from page 6 and 7, you've maybe got 2 OH groups or substituents or so on. So we'll pause and check these ones. Then I'll do 1 or 2 more examples with you for page 6 and 7 and then ask you to finish the rest. So pause the video now, complete page 5, and then replay to check your answers. Okay, so let me have a look through these examples with you. Let's find our longest chain that contains the hydroxyl group. So that is 3 carbons long. We do need a locant number because there's more than 2 carbons. And so this is prop and propan. And then again, the hydroxyl group is on carbon number 1. We number those so that the hydroxyl group is on the lowest possible carbon, and then it ends in OL. Next example, there's just 1 carbon in our longest chain, and so therefore this is called methanol, and we don't need a locant number because it could only be on carbon number 1. There only is 1 carbon. Next example, here's our OH group. So our longest chain must contain that, and that's just straight through again. There's 5, so this is going to be pentane. But where is our OH group? Well, it doesn't matter whether we number it left to right or right to left. The OH group is going to be on carbon number 3. So that is pentane, and then a dash, and then 3-OL. And then finally on this page, we have, here's our OH group. Longest carbon chain must contain that, and then we number it so that the OH group is on the lowest possible carbon, so that's going to be right to left this time. So there's 4 carbons, so it's butane, then a dash, then 2-OL. So over on page 6, I'd like to take you through the first 2 examples just because they contain either multiple OH groups or substituents as well. So let's have a wee look at the top one. So we've got 2 OH groups here, so our longest chain must contain both of those. Even if there was to be, say, a longer branch of one of the chains, it must contain both of these functional groups. So our longest chain is 3 carbons long. Doesn't matter in this case which way we number it, it's going to lead to our hydroxyl groups on carbon 1 and carbon 3. But if there was a choice, we would put those hydroxyl groups in the lowest combination of carbons. So there's 3 carbons in our longest chain. So the start of the name is propan. But then remember, we need to add an E because there's more than one hydroxyl group. Then we have our dash to indicate the position of the OH group, and they are on carbon 1 and carbon 3. Remember, if they were both on the same carbon, you would have to say put 1, 1. So you need to put the locant number of each of the hydroxyl groups, even if they're on the same carbon. And then how do we end our name? We must write diol. So not just propane 1, 3 all, it has to be propane 1, 3 diol. So remember, add the E because we've got more than one OH group, and add the di to indicate that there's 2 OH groups. Okay, let's have a wee look at the next example because we have some substituents here. And so let's find our longest chain. Our longest chain must contain the OH group. And so you can see our longest chain is straight through here, but also includes, that's been written a little bit differently just to kind of throw you off. The longest chain also includes that methyl group at the end. That's part of the longest chain. So it's not a substituent, it's part of the longest chain. Okay, we'll circle our substituents as well. We also have a wee methyl group there, CH3. Let's number the carbons so that the hydroxyl functional group is on the lowest possible carbon. Remember, the functional group gets priority over that methyl group. So this gets priority of being on the lowest possible carbon. So here's carbon 1, 2, 3, 4, 5. The names of the substituents come first, as they have done in alkanes and alkenes and halogenoalkanes. So that will be 4-methyl. And if there was another substituent, it would need to appear in alphabetical order. Our longest chain is 5, so that's pentan. There's only one hydroxyl group, so it's just pentan, not pentane. And that hydroxyl group is on carbon number 2, so it's pentan 2-ol. So 4-methyl, pentan-2-ol. So what I'd like you to do is go on and name the rest of the alcohols, remembering to find your longest chain that contains the hydroxyl group, and then numbering your carbons so that that's on the lowest possible carbon. And then thinking about your substituents as well. If there are different substituents, then you must put them in alphabetical order. So I'd like you to try the rest of the examples on page 6 and 7, and then I will check those names with you. Okay, let's check through these answers with you. Please take time to check your answers and that they're fully correct, including dashes and commas and substituents in alphabetical order. So here's our OH group. There's no others. So here's our longest chain. And you can see we have 2 substituents. We have an ethyl and a methyl group. We must number this carbon chain so that the hydroxyl group is on the lowest possible carbon. And so that's 1, 2, 3, 4, 5, 6. Substituents must come in alphabetical order. So we're going to have our ethyl group followed by our methyl group. Those numbers are just the order that they appear in the name, not their locant numbers. And you can see there's 6 carbons in the chain, so our name becomes 3-ethyl, 4-methyl, hexane, 3-ol. Check all your dashes are in the right place. Next example, you've got to be careful, we've got 2 OH groups. And here is your longest chain that contains both of those OH groups. And numbering the carbon chain won't matter, it'll be 1, 2, 3 either way. Both of these hydroxyl groups are on carbon number 2, and we must indicate that in the name. So it's propane because we have got a diol here, so we must put an E in that name. Then we put dash Then we need to put 2,2. Even though they're both on carbon number 2, and you might think it's okay to just write 2. No, you have to put a locant number for each of the hydroxyl groups. And then the end of the name is diol. So check you've got all of those details in that name. Next one, we have 2 OH groups, so hopefully you notice those. So here's an OH and here's an OH. Our longest chain must contain both of those. So there's our longest chain here. We've also got 2 substituents, these 2 methyl groups. We number those carbons so that the OH are on the lowest possible carbon. The lowest combination is going to be 1, 2, 3, 4, 5. So our OH groups are on carbon 1 and carbon 4 rather than 2 and 5. Your name then becomes 2,2 dimethyl. So again, even though the methyls are both on carbon number 2, you've got to include both locant numbers. 2,2 dimethyl pentane. Remember your E at the end of pentane. 1,4 diol because of your 2 OH groups. Over then to page 7, let's have a wee look at this one. So where's your longest chain? Your hydroxyl group is here. Your longest chain must contain that. And it's just straight across. We've got 2 substituents here. We've got a bromo group and a methyl group. And remember, they must come in alphabetical order. We number our substituents, so the hydroxyl group is on the lowest possible carbon. So don't worry about the substituents. The important thing is the hydroxyl group is on the lowest possible carbon. So that's 1, 2, 3, 4, 5. And your name becomes 3-bromo-3-methyl pentan-2-ol. And remember that your bromo must become before your methyl because it is in alphabetical order. Next example, you need to locate your OH groups, and that is here. So notice how, if you were to find your longest chain, you would maybe look this way, but that chain then doesn't contain your OH group. So instead, what you must do is put your longest chain this way so that it contains the carbon that is bonded to the OH group. And then the rest of this chain becomes an ethyl substituent. C2H5 is ethyl. So let's number our chain. That's carbon number 1, 2, 3, 4, so that the OH is on the lowest possible carbon. So this is 2-ethyl butane-1-ol. Then finally, lots going on with this last example. So locate your OH groups. There's one here and there's one here. So this is going to be a diol. Your longest chain must contain both of those. So that's straight through here. Circle your substituents so you don't forget about them. So you've got a chloro and you've got a methyl. Number your carbons so that the OH groups are on the lowest possible carbon. So that's 1, 2, 3, 4, 5, 6. Substituents in alphabetical order. So that's going to be chloro and then methyl and then the end of your alcohol name. So that name becomes 3-chloro, 4-methyl, hexane, 1,5-diol. So remember your E at the end of hexane and your diol rather than just ol. So hopefully you're happy enough naming alcohols at this point. And then just before you move on to the structure of alcohols, I want you to try question 2. So to draw the structural formula of each of the following alcohols. So maybe do that on file paper. Or you could actually do it on the back page of your booklet. I think that's blank, so you could do it on the back page or even the front page because there's a bit of room underneath your specification. And so draw those structural formula, write the name out and then draw the structure. So pause the video now and complete question 2, all parts. And then check your answers using the completed booklet of the files area on Teams. That's on the general channel, not the specific class channels. Once you've completed that, this video will take you on through the structure and properties of our alcohols. So pause the video now, complete that, check your answers, and then continue on playing the video. So let's now have a quick look at the structural differences of alcohols, and these can be classified in the same way as halogenoalkanes. So if you remember with halogenoalkanes, we were looking at the carbon that was directly attached to the halogen and then counting how many carbon atoms was attached to that. And this is a similar way with alcohols. We're looking at the carbon that is attached to the hydroxyl group And so we're looking at the carbon atom to which the hydroxyl group is bonded to, and then counting how many carbons is bonded to that. So again, we have primary, secondary and tertiary alcohols, again written with the same abbreviations. So let's have a look at primary alcohols first of all. Definition wise, which you need to know, I know it's a bit wordy, but you do need to know this definition and then be able to actually determine this in an exam setting. So a primary alcohol is an alcohol which has one carbon atom directly bonded to the carbon atom that is bonded to the OH group. So it's a very similar definition to the structure of your halogenoalkanes. So what we're looking at here, let's look at the example of ethanol. You find the carbon that's directly attached to the OH group or bonded to the OH group, so that's this one, and then we're counting how many carbons that's bonded to. So in this case, that's bonded to one other carbon atom, so that makes ethanol a primary alcohol. Then let's look at butanol. So the carbon that is bonded to the OH group is this one here. How many carbon atoms is that bonded to? It's bonded to one other, so that makes this a primary alcohol. And then methanol, here's the carbon attached to the hydroxyl group. It's actually attached to no other carbon atoms, so it is an exception to the definition, just as we saw with like chloromethane or bromomethane, but we still refer to it as a primary alcohol. So it's basically, primary alcohols are where the carbon attached to the OH group is attached to one or no other carbon atoms. And notice how essentially with primary alcohols, your OH group, your hydroxyl group, is always going to be on your end carbon in these examples, so that the carbon is only bonded to a maximum of one other. Secondary alcohols then, as the name suggests, we're looking to the carbon atom that is bonded to the OH group, and it's an alcohol which has two carbon atoms directly bonded to the carbon atom that is bonded to the OH group. So propantuol, if we have a look here, here's your carbon attached to the OH group, and it's attached to two others, and that makes this a secondary halogenoalkane. Then butanol, here's the carbon bonded to your OH group, and it's bonded to two others. That makes this a secondary alcohol. And then if we have a look at pentantuol, here is your carbon attached to the OH group, and here it's attached to two other carbon atoms. So that is again a secondary alcohol. So notice with these ones, the OH group has to be in the middle of the chain, so it can't be on the end carbon, but there's also then not an alkyl substituent on the same carbon that is bonded to the OH group. So we have to have, for example, another hydrogen atom attached to your carbon that's bonded to the OH group. Finally then, tertiary alcohol is an alcohol which has three carbon atoms directly bonded to the carbon atom that is bonded to the OH group. Find your carbon that's bonded to the OH group, and then count how many carbon atoms. Here we've got 1, 2, 3. So 2-methyl propantuol is a tertiary alcohol. And then with your 3-ethyl pentanthreol, here's your carbon attached to the OH group, and it's attached to 1, 2, 3 other carbon atoms. And note with these alcohols, you have the alcohol group, the OH group, in the middle of the chain, and then there is also an alkyl group off that same carbon. So notice the name of these. You've got 2-methyl propantuol. That means the OH group is on carbon number 2, and it means that it's also got an alkyl group, in this case methyl, on the same carbon. And notice how the name of your tertiary alcohol is 3-ethyl pentanthreol. So the OH group is on carbon number 3, as is the alcohol OH group. So if you want a bit of practice of that, you could go back to the alcohols that we drew and named on the previous pages, and you could decide whether those are primary, secondary or tertiary alcohols. Let's now have a quick look at the physical properties of alcohols, and we're going to base that on the intermolecular forces. So remember, intermolecular forces have a lot to do with the physical properties that we see in different molecules and compounds. And what we have in alcohols, I've drawn ethanol here, is because of that OH group we have the possibility of hydrogen bonding. So not only is our bond polar, so our oxygen will be delta negative, our hydrogen will be delta positive, so we could have permanent dipole-dipole interactions, but we could also have hydrogen bonding because we have a highly electronegative oxygen atom. Remember, hydrogen bonding, you need a nitrogen, oxygen or fluorine atom that is bonded to a hydrogen and can hydrogen bond then to the hydrogen in a different molecule. Hydrogen bonding is the strongest of the intermolecular forces, therefore more energy has to be put in to separate the molecules, and that has a big impact on the boiling point in particular. So due to the presence of hydrogen bonding, which we don't see in any of the other families that we've looked at so far, it's not in alkanes, it's not in alkenes, it's not in halogenoalkanes, so alcohols are going to have the highest of boiling points compared to molecules of other organic compounds that have similar RMM. Remember, similar RMM means similar van der Waals forces, so if it was just down to van der Waals forces, then they would have very similar melting points and boiling points. But we'll see that alcohols, because of their hydrogen bonding, they have higher boiling points. In other words, more energy is required to separate the molecules. So let's have a look at alcohols versus halogenoalkanes, and in particular chloroalkanes. So the main intermolecular force, the strongest intermolecular force in hydrogen or in alcohols is hydrogen bonding. The main intermolecular forces in chloroalkanes is dipole-dipole interaction. So what we're doing is we're comparing these two halogenoalkanes of the same chain length and similar RMM. If you have a look at this first example of alcohol, it's methanol, which has an RMM of 32. And we compare that to chloroalkane, the first chloroalkane that has an RMM of 50.5, that's chloromethane. So you can see the RMM in chloromethane is a lot higher, so you would expect just by van der Waals that it would have a much higher boiling point. But actually you can see it's the opposite, that the boiling point of methanol is much higher than that of chloromethane. So chloromethane is minus 24, so it's going to be a gas at room temperature. Whereas methanol is a liquid at room temperature with a boiling point of 64.5. If we compare the most similar RMMs here, so perhaps propanol to chloroethane would be its most similar RMM. Have a look at the difference in boiling point. Propanol is 97.2 and the boiling point of chloroethane is just 13. So because of that hydrogen bonding, the boiling point is much higher. And with alcohols versus alkanes, we get a better comparison of the RMM. So you can see here, methanol has a very similar RMM to ethane. This would be CH3CH3 or C2H6. But have a look at the difference in boiling point. Methanol, 64.5. Ethane, minus 88. So why is that? Because the main intermolecular force in alcohols is hydrogen bonding. Main intermolecular force in alkanes is van der Waals forces. You obviously don't need to know specific boiling points, but just be able to explain in an exam why does methanol have a higher boiling point than ethane, for example. And it's all to do with the type of intermolecular force and therefore how much energy you have to put in. So as a result, aliphatic straight chain alcohols with less than 12 carbon atoms are liquids at room temperature. Where a lot of our other organic molecules, maybe the first 4, 5 or 6 are gases at room temperature, but alcohols are liquids at room temperature if they have less than 12 carbon atoms. After that, they would be solids at room temperature. Over in the next page, you just have a diagram of the hydrogen bonding in ethanol, which you could be asked to do really from your Unit 1 chemistry in terms of drawing a hydrogen bonding. You'll note how I've drawn the shape of the OH group just as straight rather than bent or linear rather than bent, but that's just really to show the hydrogen bonding a wee bit better. But you should really, if you were asked to draw the shape of any alcohol, keep that OH group in a bent shape, and that's noted down below. But remember, with your diagrams of hydrogen bonding, you must show your lone pair on your electronegative atom. So in this case, that's your oxygen. And you must show the polarity of the bonds as well. So there's 2 molecules of ethanol that are hydrogen bonded to each other. The OH group needs to be on the terminal carbon, just in terms of space and arrangement. But you can see the hydrogen bonding there, which, as we said, requires more energy to overcome than your simple van der Waals or your dipole-dipole interaction, giving your alcohols a higher boiling point. Hydrogen bonding also has to do with the solubility. So what we find is that alcohols with short carbon chains are miscible with water, and your definition of miscible is there. Liquids which mix in all proportions to form a single layer. And that's again due to the ability of alcohols to form hydrogen bonds with water molecules. So they are able to break up the hydrogen bonded structure of water. We saw with chloro and bromoalkanes, even though they have dipole interactions, that's not strong enough to overcome the hydrogen bonding of water. So it doesn't break up water molecules, so they're not miscible. However, it is important to note that the rest of your carbon chain is non-polar. So therefore, if you have got alcohols with particularly long carbon chains, then the solubility of your alcohol is going to decrease. So as the carbon chain increases in size, the solubility is going to decrease, because it's only really the OH group that can hydrogen bond with the water. And so therefore, if you have a really long carbon chain that's non-polar, can't interact with water, then your alcohol may be insoluble or immiscible overall. Here you've got a diagram of your hydrogen bonding in ethanol. So the O of your ethanol can hydrogen bond to the hydrogen in water, and the hydrogen can hydrogen bond to the oxygen in water. And then finally, if we could take a really brief look at the production of alcohols, because we've actually met these methods in our alkenes and our halogenoalkanes topics. You'll be glad to hear that there's actually only 2 methods of preparation of alcohols that you need to be familiar with, compared to your 6 for halogenoalkanes, and there's not a big detailed practical method for that as it was with halogenoalkanes. So how can we produce alcohols? You're thinking back to your previous topics. So you're trying to link all your learning from these different topics. So from alkanes, alkenes, and halogenoalkanes, and now your alcohols. So if you remember back to our halogenoalkanes topic, if we get a halogenoalkane and we heat it under reflux with aqueous sodium hydroxide, remember that this is a hydrolysis reaction. And we looked at that mechanism in detail in Unit 2.5, so that you can look back at those notes if you need the detailed mechanism of that. But this is a method of preparing alcohols. So from the halogenoalkanes, you could be asked it in the context of a reaction of a halogenoalkane. From this topic, you could be asked it in terms of the method of preparation. So it might be, how do you prepare butane 1-ol, as there is here. So you can see what we're doing in this reaction is we're swapping our halogen for a hydroxide ion, and that gives us the corresponding alcohol. And then if it's catalyzed by an alkali, and then we'll get the salt of our halide ion. So here we're converting the corresponding halogenoalkane to the corresponding alcohol. The reaction type is hydrolysis, catalyzed by an alkali, and the mechanism is nucleophilic substitution, but remember we could have SN1 or SN2 depending on the structure of your halogenoalkane. So just choose your corresponding halogenoalkane from the alcohol that you want to produce. So if you want to produce, for example, propan 2-ol, then you would need to start with a corresponding halogenoalkane. So you would be swapping that OH group with, say, a chlorine on that particular carbon atom. So you would be starting with 2-chloropropane, for example. So always choose the appropriate corresponding halogenoalkane. Finally, we can also produce an alcohol from the corresponding alkene using steam, and this is done industrially in the production of ethanol. So ethanol, in terms of use in alcoholic drinks, would be prepared using fermentation, which you learnt at GCSE. But we're just looking at the industrial production of ethanol here, the reaction of ethene with steam. And this, again, is looked at in more detail in your unit 2.4, but it is made by the hydration of ethene because we're literally adding water. The catalyst, you have to know the conditions for this, so you need to know your catalyst and your temperature and your pressure. So phosphoric acid on a silica support is your catalyst. Temperature is 300 degrees Celsius and pressure is 60 atmospheres. Again, we learnt this in our previous topic. So this reaction type could be called hydration. You can also refer to it as an addition reaction because we're taking two smaller molecules. So in this case, ethene and steam, in other words, H2O, and we are adding that across the double bond. So this is an addition reaction. Remember, alkenes are susceptible to that because the pi bond of the double bond is weaker. So it can break, allowing these two carbon atoms to form an extra bond with something else. So the hydrogen of the water goes to one carbon and the OH goes to the other carbon. And what we've ended up with is ethanol. And what you could do in the bottom of page 12 is just add a note on your third method of preparation, which they don't tend to ask as much at A level, but you can, they could refer this back to GCSE knowledge. So if you remember from that reaction, we essentially take some plant sugars, in particular glucose, so glucose from plant sugars, and we ferment that, so in the absence of air, using yeast. And this is a method of preparing ethanol on an industrial level, but it produces ethanol in quite a low concentration because at higher concentrations the ethanol kills the yeast and stops the reaction. So this is done under warm conditions, around 35 but no more than 37 degrees, because otherwise that would kill the yeast as well. So you can look back at your GCSE notes for that. As I said, generally it's not really asked as much at A level, but if that does come up, I think it might come up once or twice in your questions at the back of the booklet, so just so that you're familiar with that. So that finishes the first section of alcohols. So we have looked at the general formula of alcohols, their functional group, naming alcohols, their different structures, primary, secondary and tertiary, their properties and also their preparation. So that's a good bulk of the topic done, and what we need to then complete afterwards is the reactions of alcohols.